So continuing our DSA course, let's try to understand this problem. Like this would be some kind of a because this problem is some kind of a theory problem. So yeah, we will take it in that direction. So first two docs and understanding about heaps is necessary as a point of your obviously implementation questions or yeah, implementation questions are generally can be asked in some interviews where you could have just they would just say to implement the heap. Okay, so or basically they ask you some properties around the heap. So only in that scenario that would be helpful. But yeah, understanding about that, like no one can be certain when this gets asked. But obviously knowing this will help. So converting min heap to max heap. Okay, so the whole idea about this problem would be that you are given a min heap. Okay, and min heap is not itself like how you process it. You yeah, you would know that heaps are basically kind of a tree structure first of all, but they are represented through arrays. So how it will be represented, let's say my first node root node is, let's say, having a value something 10. If this is the root node of a min heap, what does this signify? That every value in the min heap would be greater than 10. So there would be two children's. It will be, let's say, 11 and 12. Yeah. Now they would have some children's. Now what is the property about the children's? The property would be that yeah, they would be greater than the value of node. That is one property that you have to satisfy always. Let's say it is 15 and 18 and 20. Okay, it's not like kind of a binary search tree that you have to maintain. It's just like only thing that you care about is that parent should be greater than node, right? Yeah, parent should be lesser than the yeah, children's. So that is one thing that we care about. Now if I have to insert something into this min heap, okay, let's say this value I want to insert is 5. Where you do you think it will go? 5 is the lowest value, so it should become root, right? So what we do, we compare this 5 with 10. Hmm? And basically or what we do, we just push 5 at the end. When we push at the end, so currently this looks like 10 and 11 and 12 and 15 and 16 and 18 and 20. So when I push it, it will get pushed over here. As you can see, this is complete, right? Yeah, one property about this is that they looks like a balanced tree. This is a balanced tree. As you can see, there are 7 nodes of perfectly balanced. If I push something like 5, it will come as the children of 15. Okay, now yeah, because of the indexing, how indexing goes, due to that, it will come as the children of 15. Now what we do, we have just done our work. We had to push 5, we pushed 5. Now the heap process will start. Heap will see, okay, 10, it is fine with 11 and 12, or it will pick up the yeah. So then basically we will call on, let's say, something 11 or 12 or yeah. Then it comes on, let's say, 15. 15 just says that okay, my children should always be lesser than, no, lesser than, greater than me. So if 5 is there, so you see what is the smallest value. Smallest value is 5. So 5 goes over here and 15 comes over there. Okay, so basically previously we said that okay, 5 is a children of 15, but 15 says no. um, 5 is parent of 15, 15 becomes now children. So similarly that goes with, let's say, 11 also. 5 comes up, then 10 and 5 see, like 10 see that okay, his children is 5 and 12, so yeah, that 5 comes up. So one thing we can see that for doing a work for root, you should have already done the work for the below nodes. So that's how it recursive it is, or that's how like topo sort you can also say. But yeah, basically recursive, that you must have solved the later with the subtree before solving for the root. After that, now you see that this is perfectly fine, and that's how your min heap will look like. But the purpose of this was not this. Purpose of this was to convert this to something like max heap. Now, how would max heap look like? So that's how the conversion process goes. So for I'm saying like for processing the root, you must have processed all the children down below. So if I just take you back to where we were initially, I think we were over here. Now to process the root, let's say I process 11 first. 11 and then I process 15 first. 15 and as a like single node it's fine. 16 as a single node it's fine. But when I talk about max heap, 16 would come here and 11 will come here. Okay, fine. Now this part is fine, looks fine. Now what about this part? 20 will come over here. Yeah, so 18 is fine as of himself, 20 is fine as of himself, but 12 is not fine as a max heap root or yeah, root of a max heap subtree. He will swap with 20 and yeah, gets the 12, 20 over here. And similarly, this 10 would not be feeling good over here, so he would swap himself with this 20 and 10 would come over here. Now again, this becomes somehow like 18 will come up and 10 goes down. So I think it's a two-way process. First, you process the root, the children nodes to get to the root node. Then once the root comes down, then again you call on this. That is very important. Whenever you do a change, so let's say this node got changed. Now you call on the yeah subtree of it, because this became 20 from 10. Okay, so with respect to 10, this tree was fine, the subtree was fine with respect to 10. But what about 20? No, 20 के लिए sorry, what about yeah, this was fine with respect to I think 20, not fine with respect to 10. Okay, whatever. So now I think this would be the max heap for that. Now let's consider what the example they are giving. And just quickly tell me what will be the max heap for this, you would think like. Just do it over here. So if this is 359, so as I say that first we go down till the leaf nodes, all the leaf nodes are fine and themselves. So 12, 18 comes up, acha, and I think 8 has a children 9, right? 6 has a children 1, 6 has a children 18, I feel. Yeah, 6 has a children 18, and then 8 has a children 9. So 18 comes up, okay. Then 5 and 8. Okay, who has this children? 8, 5 or 9. Oh, this is so messed up. Ooh, now it looks fine. Okay, so this is the structure. So first of all, 18 will come up. There's a 5, and this is a 9, and this is a 3. I think that should be fine. Okay. Okay, fine. So now first of all, 18 comes up, and 6 comes down. It's fine as of now. Similarly, 8 comes down, 9 comes up. Now 18 comes up again, 5 comes down. Then over here 20 comes up, 9 comes down, and 20 comes up, and 3 comes down. Now 10 comes up, 3 comes down. This is the heapify process. Anything else? I think it's fine now. But why is this 18, 5, 12? How the 5 came? Oh, 5 came down. 5 came down, so that also you need to process. I think 6 was there initially, and 18 went up. And let's say 5 will come here, and this will become 12. And now it looks fine. If I say what will max heap will look like, 20, 18, then 10, then 18 has a children 12 and 9, and 10 has a children 9 and 3, and 12 is the children 5 and 6, 9 is the children 8, and yeah, that's all. So everyone is fine with respect to their children, so the heap is fine, we can say. So answer would match 2018 till 99. Yeah, it looks like that only. But how to create this? I think it is a two-pass solution. Two-pass in terms of like how we are going down and up. First, we called on this root node, then root node called on this left part, right part, this call on the 6, and whenever the call goes on 6, they call on say 12 and 18 are fine, and then you found out like, okay, which is the largest? Are you the largest? Are you the largest? Are you the largest? 18 says I'm the largest. Okay, just swap with the largest and make this and call on 6 again. Okay, then basically down from 6 there is nothing, so it's fine. And now 18 and 5 and 8. Now as like this node got like 5 called on this part to give me what, to just called just to have everything sorted, and now everything is sorted, like 18 is there, and now it will compare, 5 will actually compare the value, and then we will actually like do some swapping if it is required, and wherever we did swapping largest, okay, 5 comes over here. Now again I called on this, okay, and you know the process of calling on that. So there is a function which uh, this is thoda sa bit to remember that heap arguments you pass on the node, or basically id index, yeah, which you want to, which is points to the root of your subtree, and then yeah, I think it's fine. And then you obviously need a vector, obviously, which is there. And third thing which you need is, three things are needed. I think first two of them are these. So basically what we do, first of all, we say that because id is needed to identify left and right, but for everything in general, lf is equal to 2 into id plus 1, rg is equal to 2 into id plus 2, and then you call on heapify process, okay, on left part, and you pass your vector, and then you call on heapify process on your right part, you pass your vector. That would make sure that, okay, elephant, so basically, yeah, like the value of the not, yeah, the value of elephant rg, um, this will make sure that they has correct value. Now I need to make sure that after they have, my children have correct value, I should have correct value. And you say int largest, this is the some kind of a storing index of the largest element down like in the subtree, not in the subtree but among these three things, which is id. And you just say that if my left is greater than not left but yeah, v of left is greater than v of id, then my sorry largest, then my large become whatever large become equal to left. Then I compare it with my right part. If v of large, I mean v of right is greater than v of large, largest, largest becomes equal to right. Yeah, there's now there is no, yeah, now you got the largest for sure. That is for sure. And if you now what we will do, that we will say swap v of id to v of largest. Some cases that might be already the largest, so now that part is sorted. Now if that part is sorted, largest is still that index, right? Okay, you swap the values, but id was smaller than root of the string. So but the subtree, right? I was sure that the root of that subtree is actually the largest among that subtree, but I'm not sure if id qualifies to be the root of that subtree or even not that. Like, because currently id was the root of the subtree, which signifies that id was largest, but we found out that id was not the largest, so we swapped it id with something, so id is now that part, and then we called on it. Like, this you only do, I think this part you only do if your id is not equal to largest. Okay, if large is not equal to id, right? Because id is fixed. Id is fixed. Largest is not equal to id, so I swap. First of all, I take the maximum value to my id, and then I call on large. Large is basically, uh, that index which was where now id goes. And you need a vector. So this is the two paths. Like, first you do stuff here, then you can do stuff for yourself, then you do stuff down from you. Okay, but just due to the nature of balanced, it is getting added up. It's not like multiplication of time complexity, it is just addition of time complexity. So that's how, like, n log n plus n log n is again n log n, that kind of thing. So that is, I think, which we will need. This is the main thing. For each non-leaf node we perform a heapify process. You know, when heap this portion, larger of the children. Yeah. So first we say large equal to I, then we say if L is greater than I, largest becomes L. Or you could have just say if L is greater than largest, largest becomes L. If now R is greater than largest, largest becomes this. If largest is greater than not this, swap and do a heapify process. Three things which you pass is array, your ID, and N. Oh, okay, N is required for like every other thing, but you can also find N using the size of the heap. N is just a constant, man. Hmm. So that's how heapify process goes. Like, and for as far as this question is concerned, for like say heapifying all the nodes, you need to start calling from n minus 2 till 0, because sorry, n by 2, don't know why n minus 2 by 2. But yeah, there is like half of the nodes. Why I'm saying this, because as I said that only half of the nodes will be there which does not have children's, okay, which are like, yeah, which have children, sorry. So over here if you see which the last node that have children is 12, 9 and 10. These are the three nodes that have children, or that could be in a way, because the, let's say, length, whatever this is, yeah, every node has two children, okay, every node has exactly two children. So I'm only looking for the node that has children. So this node has two children, this node has one children, this node has two children, okay. But the main idea of this is that, okay, when, yeah, this is like the last node whose children is this, like it is id by 2. If you want to find, let's say, for id who's your left children, right children, you do 2i plus 1, right? 2id plus 1, 2id plus 2. For id, you want to find who is this parent, you do id divided by 2, simply id divided by 2, or id minus 1 divided by 2, something like that. So that is what they are doing, id minus 1 divided by 2 or id minus 2 divided by 2, to just, yeah, from the internal node rightmost, bottommost, rightmost internal node, and heapify all the internal nodes. So that's what max heapify process that you need to run sometimes, and that will make sure that, yeah, your, because heapify is like processes that only, that you are given array which may or may not be a heap, but you created a heap. Yeah. Okay guys, that's about it. Bye.